My dear students, in the last class we discussed about the permutation groups and then we try to solve some problems. Now today we have to move to the important class of a group is a dihedral group, about the symmetries. So one can construct a group from any geometric shape by the symmetry of it. The symmetries are the transformations such as a rotation and reflection that maps that shape onto itself. So it looks the same before after these transformation. The group of all the transformation under which the object is invariant is called the group of symmetries. When the shape is regular polygon, the group is called is the dihedral group. Uh, Very simple uh, way we have to just say that if we take a I just say that if we have to some rotations and the reflections. For example, we take some triangles into there and we have to just take if we have to rotation is a 0. So if we have to just say that is a 1, 2, 3. If we have to rotate about the 0 angle, that means this is simply is equal to not no change. And if we have to, this is again we have to rotating into this. So we have to, this is equal to 1, this is equal to, you have a 2 and this is equal to 3 again, but there is a change and then again this is not a rotation is through this way, we can just write into this. So simply we can say that we have to any geometrical figure, if we apply this geometry figures by the rotations or the reflections, for suppose we have to like this and we have a this, we have to just reflecting this into this. So you have a dust is equal to 1, 2, 3 after reflections. This should be into this like look like this form, and then we have to, this is equal to 1, this is equal to 3 and 2, then the shape remain the same. So symmetries we can just say that so it looks same before and after the transformations of rotation and reflections. So this is very important when you have a using in the applications of this group symmetries of a group in the chemistry. We have to study is a regular polygon of a groups, and that regular polygons of a group is called a dihedral group. So the definition is simply the nth dihedral group denoted as a Dn is a group of symmetries of regular n again or n is equal to greater than or equal to 3. We have just say n polygons, so n and gone. We have to denote it as a n is always is the greater than or equal to 3. We have to just say that we have two types of operations is a rotation and the reflection. So when we look the symmetry of a regular and gun, the identity simply is the transformation which make no change is called is the, we have a identity. So if just say we have to just we have to take a, for example, we have to take this square and then we have to square is equal to, we have a b c d and then we have to about the 0 angle, then this is remain the same. In this case you have a identity. Now if we have to just if we have to just rotated this is about the or 90 degree, then you can just say that this is the square looks like is this. You have to, if you rotate it, this is a 90 degree, so this is equal to D, A, B and C, and if we again rotate this is equal to 90 degree, then I rotated this is equal to 180 degree. So we have to like this, we have to like, you have a D, A and BC, this is 1 180 degree, the same, and then this is r 90 degree, and then if we have to, this is again rotated about, this is a 270 degree, so we look like into the this is equal to D, A and B, and we have a C, and this is R equal to, we have a 270 degree. So we can simply say that this square we have to rotate it as 0 degree, means we have a simply is a transformation making no changes, and then we have a identity, or in general we can say that theta can be rotated as a 360 degree over n of n polygons. So we just this is the this are the only 4 possibility of a rotation of this, because if you next rotation we have to getting the again the identity. So this are the rotations we have to making change. So we just denote it as r0. We have to r0 for this example, and then we have a r90, then we have a r180, then r we have a rotation is equal to 270. If we rotate the 360, then again we getting the r0. Now we have to reflections. So just I just rotations. Let the size of the counterclockwise rotation r is theta is equal to 360 by n. Then these there exist n rotations because we have to r square, r3, r to the power n, and this generally we denote it as equal to r0. Then we have for our example this is r 90 degree, so we have to rotate about the 90 degree, then we have to again the same shape, and then we have to positions ourselves. So next possibility is there, we have to have a reflection. So reflection means simply we have to take a square is a same example as a square. So we have a B C D, then we have to reflect it about the horizontal axis. If we have to reflect, this is about the horizontal axis, so you have a figure is look like it. This is the same figure, but there is a D, C and A, B after this, and also we have a reflection about the possible is equal to. So we have a B and C, D, and then we have a vertical. If we have a vertical, so this is equal to this, and vertical if we take a vertical, then we have a so we have a simply is equal to, we have a B and C and A and D, and then another possibility of this reflections, you can say that by the also we have a position into the diagonal 1. So this is equal to A, you have a B and you have a C and you have a D, and this look like as again is a by this diagonal we have to just say that. So we have a B, D and A and C, another by this again with the another diagonal number 2. So we have a B, C, D, and this is look like again we have a into this form, and that is the form of a is this is equal to, you have a D, B and C, and you have a. So we have a for this square we have a clearly we have a rotations are r0, r90, r180, r270. So we have a 4 rotations, and we have a clearly you have a again this is equal to 4 reflections are there. So consider the reflection f with the respect to the vertical axis. Then there exists 2 reflections f square is equal to, again if we have to getting the again reflected this, so we have getting the identity element. So we just said that the remaining symmetries can be obtained by the combination of a r and f. By this combination rf we have a one symmetry, r square f we have a, because this is r to the power n, we have rotations are r to the power r to up to r to the power n minus 1 rotations, and then we have a f. We have a f square is equal to identity. So we have the combination of a rf, r square f, and so on, r to the power n minus 1 f we have to. So we have to combining this all r and f, we have to calculate the all the symmetries of a such a figure, geometrical figure we have to write in this form. And now for general, we just say that, for example, we have a n rotation of a roll. So r0 is equal to, we have just as identity, and then r is equal to, we have a 1 2 n minus 1 minus 2 n. Then we have a rotation like this. So 1 goes to 2, then the 2 goes to 3, and up to n minus 1, and then last one is equal to the by the cyclic notation. Then we have to take r square, then we have to again we have to go into this, then r to the power n minus 1 is equal to, we have to again in the form of this. So we have a n up to, similarly we go to n 1 and to so on, and then we have to again, if we have to going to the r to the power n, and then r to the power n, similarly we have to getting the identity. So if we have taken the similarly r to the power n, then if this is a rotation is given the 1 2 up to n minus 2 n minus 1 n, and then we have to 1 2, we have a n minus 2 n minus 1 and n, and that is nothing but is equal to r to the power 0 or I, or we can say that into the identity. So in general, we have a n rotation of a n polygon in a such a way. Simply we just said that it is clear that this, if is the r to the power n is equal to identity. So we can simply say that the order of this rotation is clearly n, such that if order is equal to n, then r to the power I, r to the power j can be written as r to the power I plus j, and r to the power I inverse is equal to same as r to the power n minus I. So where I lies between 0 to n minus 1. So here 1 r square up to r n minus n is an abelian group of order n under the composition. So the rotation forms a cyclic group generated by R. So this rotations is a clearly is a form a group under the composition. So we have to just say that all this composition, you can just say that order of n is equal to. So this is generated by R. So generated by clearly R. So this is r to the power n is equal to, we have identity, then all the elements of R. So this rotation form a clearly we can say that this form a cyclic group with this with generated by the element of a R. So we have also n reflections, because we say that there is a two types of things we have using this rotations and reflections. So we have to already show that for R order of R reflections, n reflections are there, and then order to the power n is equal to order of this reflections is n, and then this is a group, as an abelian group, form an abelian group under the of n order n and under composition, and this rotation form a cyclic group generated by R. Now we have to again we also have the n reflections of the regular polygon. So we have a we have to this reflection, we have a f1, we have to write in the fixing 1 and then reflecting this, and then we have a this way. So we have a 2 goes to n, and then 2 and reflecting, and then we have to rotate this. Again we have to just f2, we have to getting f2, then we have to simply we have to writing this, and then we have to again using the notation for this, 1 goes to 2, and then 2 goes to 1, and then we have to again the 3, and then fn is equal to, we have a n minus 1 and so on. If we taking again, so we have a fn, similarly we have to writing into the this form. So we have also the n reflection of a regular polygon into such a way, f1 we have to write this form, f2, and then we have to rotating reflecting reflection of a this into a this form, f of n is equal to f of clearly f of n, then 2n minus 1, n minus 2, 3, 2, 1, and then we have to again we have to writing into this form. If we have to go to the 1, then we have to this is going to n, then we have getting the this f1. If we take again f of n plus 1, then we have to getting the this f1 again, reflection of this we getting the f of 1 is there. So it is straightforward to verify that fj square is equal to 1 and for example, you just take a, I take a 3 elements, so you take a 1, 2, 3. So this is 3 and 2, and then we have to reflection of this. Now I say that this f I square is equal to identity. So we take a this f of square is equal to f composition f, and this is equal to, you have a 1, 2, 3, 1, 3, 2. And then 1, 2, 3, 1, 3, 2, and then you have a 1, 2, 3, 1 goes to 1, 2, 3, 2, and then 3, 2 is equal to 3, then you have to get getting the identity. So this is means we have in the cyclic notation we looking at 1, 3, 2, then clearly f of inverse can be written as a 2, 1, 3, and this is the same as a 1, 3, 2. So this means clearly we can say that f inverse is the same as a f also. So it is straightforward to verify that f I square is equal to identity and f I inverse is equal to same as a f of I. So we have to dispatching this rotation and reflections in our next slides illustrate how that that a rotation preserves the order of indices around the regular and gun, while the reflection reverse it. This observation leads the following properties. Means we have a rotation into rotation is equal to rotation, rotation into reflection is giving reflection, reflection and rotation again reflection, reflection we have to getting rotation, rotation inverse is equal to rotation, reflection inverse is equal to reflection. Means we can simply say that inverse of a rotation is a rotation, inverse of a reflection is a reflection, and we have to take a rotation or rotation composition, then we have again is a rotation, rotation and reflection composition we have given the reflection, and reflection and rotation is again reflection. When we take a composition of a reflection and reflection is giving you as a simply is a giving as a rotation. So now we have to just say that by this the set of n rotations and reflections form a group of order 2n and known as a dihedral group Dn. So we have a because we have a n rotations and reflections, the total we have a order of the group is equal to we have a 2n, and then we have to just say that, and that is called is the dihedral group of order dihedral group of Dn, and then order of a Dn is clearly is equal to, we have to just say that is equal to 2. The dihedral group Dn is a relatively small subgroup of the symmetry group of Sn, making it an essential example in the study of group theory. So let R be an arbitrary rotation of order n and f be an arbitrary reflection in Dn. So we just say that we assuming that R be an arbitrary rotations and n be a f be a arbitrary reflections in Dn. So if order of n, then r to the power n is equal to, we have to getting this identity. So we just say that 1 r square r to the power n minus 1 are distinct rotations in Dn. So we can just say that the indices I and j lies between 0 to n minus 1. So r to the power I composition with the reflection f, and is the same as a r to the power j composition with the f. So this means by the this cancellation law, we can say that r to the power I is equal to r to the power j. If r to the power I, r to the power j, then I and j are the same. So we can say that simply r to the power I f, r to the power j, I is equal to j. So means we can say that f, rf, r square f and r to the power n minus f are distinct reflections in Dn. So, clearly we have to just say that if these are the two same, then only possible is this. So, this means in this case r f, and if we have a r square f, and all are the distinct reflections in Dn. Thus, we have two and different symmetries for the regular and gun, and Dn is defined by 1 to r minus 1 we have a rotation, and f, rf and r to the power, and this is are the reflections. So, for the I take one example for this square, or we take a examples, some example for square we have to taking examples. So, if we taking the examples of a square, I show that there is a the reflections we have a this I just take this reflection is equal to A, B and C, D, and this is reflection is we have a rotation about 0, and then we have to 0, we have a rotation about the 90 degree, then rotation about 180 degree for this R, and then rotation what I 270 degree. So, this is we have a 4 elements are there, and then we have these are the reflections. So, this is rotations, sorry, this is a rotations, and now we have a reflections along to the, we have to just say that this with the horizontal, and then we have a vertical, then diagonal 1 and diagonal 2. So, we have a 4 reflections are there. So, we have to just, this is a clearly by this is our Dn in this case of a this is square. So, later on I just show that this example in the details how to we have to construct this by rotation and reflection by geometrically, and then we have to prove that this satisfies all the properties of a group, and then we have to show that this is clearly is a group Dn. So, this is the way we can, the Dn is simply in the form of this. So, we can simplify this, we just because if you see here since Rf is a reflection, so if we take a RF composition is giving the identity. So, thus we have the following important relation in the Dn, F inverse is equal to, because we have a inverse of this is the same. So, F and this is equal to, we have to just say that is the same as a R inverse. So, we can say that simply the further implies that we can in general F r to the power I f is equal to F r f. So, this is clearly we can say that f of r square f can be written in the form of f of rf, and we have to rf, and then you have to f of rf. We have to using this condition, and then we have to some this is r square, simply we have to prove into this form. So, we have to if you remember, we have to group, we have to just so h to the power I. So, we have to just say that f r f to, for example, square, and this is can be is equal to, can be written as the form of a f r f, and then f r f, and then we have a f r f square, then you have a r of f, and f square you have a identity. So, f r square f, then we have a simply in general we can say that into this form, and then we have a, it's the same as a r to the power inverse also there. So, which can be written in as a, if this we can say that by this we can say that f of r to the power I f is equal to r inverse. So, this means r to the power minus inverse of I, then f we can write f r in to the power I f into f inverse. Then we have a we have to just because inverse of f is equal to itself. So, simply we have to write into this form f of I inverse, F inverse is equal to F. So simply F of Ri to the power I R to the power minus IF, and we have to together with the reflection R to the power n, F to the power n is equal to, we have a identity. So in Dn, so we can rewrite any product of R and F in the form of R to the power I, F to the power j, where I lies between to n minus 1 and j is equal to 0 and 1. Therefore, we can write in general standard notation of a Dn of a dihedral group is R and F, rotation and reflection, where R to the power n, F to the power n is equal to identity and RF. And so if we have to simply, if we have to write D3, D3 is nothing but is equal to, we have a rotation and reflections generated by this such that R to the power 3 is equal to F square is equal to identity, and R of F is equal to same as R to the power 2. So we have to writing into this condition, and then in general we can write any dihedral group Dn into the form of this, and total number of element of this size of this Dn is equal to, we already show that this is equal to 2 of n. So clearly we have to just say that Dn is a non-commutative. In general, R of F is not equal to F of R. So rotation into this we have to just say that so clearly generally R F is not the same as a F of R. So we simply say that these are the clearly this is the, now I just give the example of a dihedral group of a D2. Now we have to consider the rectangle that is not a square. We have to this figure. Now we have a, I take a 1 2 3 4, and then we have to A, and this is a B, and this is a C. This is the because D2 is equal to we have a size of a D2 is equal to 2 into 2 is equal to 4. So this is clearly there is a 4 elements of this group, and then I assume A, E, A, B and C, and then you remember we have to A square, B square, C square is equal to identity, and then AB is equal to, we have a C, and we have a AC is equal to B, and we have a BC is equal to A. Like this, if we have to just take a into this notation where E is equal to ABC, where A represent the counterclockwise rotation. So we have to A is the rotation of the rectangle about the x-axis. So A is about the x-axis at 180 degree, and then we have to B represent the counterclockwise rotation of rectangle y-axis at 180. This is y80 again 180 degree, and then we have to C represent the counterclockwise rotation of the rectangle about the z axis, the axis coming out on the origin toward you by the this origin, and then we have to rotate it this again C as a 180 degree. So you see after this we have to the element ABC satisfies the relations, this AB BC is equal to C, and then this also satisfies this condition, and the binary operation is a function of a composition, mean is successive application of a rotation, and by labeling the vertices of the rectangles as 1, 2, 3, 4 as shown in a figure, we can define each rotation as a permutation of the set 1, 2, 3, 4. So each rotation we have to just say that if we have a rotation about the no rotation, so this is identity, there is a no rotation, and then if we have to rotate as a about the x-axis 180 degree, then we have to this means we have to clearly we have to like A is equal to this, and then B is again rotated about the 180 degree. So this is like into this form, and C is because you just see here we have to just say that we have to like sorry, this way we have a like this 1, 2, 3 and 4. So, if there is a no rotation, so we can say that is identity. Then we have a, if we have a like this, so this is a rotation is a B, this is a rotation is A, and this is a rotation of a C is there. So, if you have to rotating, and this is equal to 180 degree, so you have a so we have a we have to just this, so you have a 1 goes to 1 is changes the 2, and 2 changes the 1, and 3 and 4 also. So, this means if we have to rotate it, this is 180 degree, and then if you rotate it is 180 degree, then this should be this flipping into this form. So, we have to getting A. Now, we have to this about the this. So, you have a 1 and 4, and then 3 and 2 is a flipping, and then this again we have to define into the now first one is this, we have to rotating, this is equal to 180 degree. So, like this, and then again we have to rotating is 180 degree, and to this is equal to this. So, this means simply is into this form. Now, C is rotating about the this center. So, if it is center, then 3 and 1 and 4 and 2 are interchanged. So, then clearly we have to getting this E, A, B, C are these are the permutations. So, E is equal to we have a identity, A is equal to you have a 1 2 1 2, and then you have a 3 4, and B is equal to you have a 1 4 and 2 3, and C is equal to you have a 1 3 and 2 4 are the permutation. Now, if you take a square, then clearly you take a square. If you take a square, 1 2 3 4, 1 goes to 2, 2 goes to 1, 2 goes to 1, 2 goes to 2, 3 goes to 4, 4 goes to 3, and then you have a 4. Then clearly this is equal to identity. And similarly, you have to show that is a B square is equal to identity, and C square is also identity. So, satisfy this, and then now we have to check A and B, A composition B. So, we have a 1 2 3 4. Now, A composition B. So, 1 goes to 4, 4 goes to 3, 2 goes to 3, 3 goes to 4, 3 goes to 2, 2 goes to 1, 4 goes to 1, 1 goes to 2, and now you can see this is 3 4 1 2, this is equal to C. So, this is satisfy the whatever conditions we have to writing it here. So, this means for instance we have to calculating A B is equal to C, and similarly V is equal to A is equal to rotation, B is equal to F, and C is equal to we have to giving you the simply is equal to. So, A is equal to we have giving the rotation, B is giving we have a reflection, and C is giving the composition of a this 2, and the Cayley table for this V under the permutation of show is here, and this is a group known as a group of symmetry of a rectangular D2, or we already discussed this group previously, and this group is called is a Klein 4 group, and note that this group is an abelian. So, this group is a note that this group is a abelian, because every group of order less than equal to 6 is always an abelian. The first non-abelian group is order 6. So, next so I think I have to stop now, and we have to continue discussion of a Dihedral group into the next class also. In next class, I try to discuss the 2 more problems of this Dihedral group, symmetry of a triangles and symmetry of a squares. So, I have to stop this lecture here and then continue in the next. Thank you.